Welcome to CCAI
321 Artificial Neural Networks, Week 7. So, in this chapter, we're going to look at multilayer perceptrons, several examples, function approximation using artificial neural networks, the backpropagation algorithm, batch versus incremental training, and using backpropagation along with several examples. So this is what a multi-layer perceptron looks like. In this case, is an example of a 3-layer network. So this should be familiar to you by now. Only the first layer, of course, receives the input vector P. Each layer has its own weight matrix, and each layer has its own bias vector. We will be using superscripts for the weight and bias matrices and vectors for the output vectors of each layer to represent the layer number. So these are not exponents, should not be confused with exponents in this section at least. So if the first layer has R inputs and S1 neurons, that means that the weight matrix will have dimensions S1 by R, and the bias vector will have dimension S1 by N. Similarly, the intermediate output N1 of the first layer that you see over here, and the output from the activation function of the first layer, F1, will both have the same dimensions, S1 by 1. And just like that, the output of the first layer, denoted by A1, will share the same dimension, which will then, of course, serve as the input to the second layer. The second layer may have a different number of neurons in it, say S2, which means that the weight matrix of the second layer will have dimensions S2 by S1. And we denote the weight matrix, of course, by W with a 2 in the superscript. The bias vector will, of course, be S2 by 1 in dimension and be denoted by, again, B with a 2 in the superscript. And, of course, intermediate output N2, function, and output of the second layer A2 will all share the same dimensions, S2 by 1. The output from the second layer in turn becomes the input to the third layer, and the third layer may contain yet another different number of neurons, say S3, making the dimensions of its weight matrix W3 S3 by S2. Bias vector is S3 by 1, intermediate output function and final output of the third layer will all have dimensions S3 by 1. Now, a single layer neuron, as we now understand, cannot classify data like you see in this figure up here. A problem like this will require at least a 2-layer neuron. And so we'd need 2 decision boundaries to separate the 2 inputs that we have in the lower left corner, and we can do that with 2 decision boundaries like this blue one and this red one over here. By now you should understand how to find these decision boundaries. Pick 2 points on these boundaries, say 0.50 and 0.51. I believe that's 0.51 in this one. This example doesn't show the scale. I think that's actually in this particular example, this is 0, this is 1, this is 2, and the y-axis has a different scale. This is 0, this is 0.5, and I believe this is 1, as we'll discover. So we can pick 2 points, say this one over here, and 0.51 would be this point over here. Pick 2 points, find the distance vector, the vector between these 2 points, in this case 0, -1. Find a vector that's orthogonal to that, -1, 0. So that makes it minus, so basically in this puts it's a vector in to the left side and a 0 along the y-axis. So that's a vector pointing this side. Or if I draw it along with the decision boundary, I can draw it like this. That's how you'll see it drawn in many of the other figures that are to come in this chapter. The weight matrix over here becomes -1, 0, one that is orthogonal to the distance vector between the 2 points B and A. We just need the bias, which means we can just pick any point on that line. So 0.5, 0.5, that's this point over here. We pick that, put that into this equation. We have weight, we have a point P on the decision boundary, which allows us to compute B, in this case 0.5. And we repeat the exact same procedure for this red decision boundary. Pick 2 points, one at 0.75, that would be around here. The other point at 0.75, that would be over here. The distance vector between those two is -2, 0. A vector that's orthogonal to both is 0, -1. Of course, there are many possible choices over here, and we want anything to this side of the decision boundary, because this is the side that these two inputs are on. We want the weight matrix to point in this direction, so 0, -1, 0 along the x-axis, -1 along the y-axis, so pointing downwards. As you can see, 0, 1 would have also been an orthogonal vector, orthogonal to this distance vector. That would have also worked otherwise. But for reasons that will become clear in a little bit, we want the black, these inputs over here shown by these black dots, we want them to be on the positive side, on the side of the decision boundary, for which these values will evaluate to 1. So to a positive number, I'm sorry. Okay, so we have, again, we find weight matrix, use the same, pick a point on anywhere on this decision boundary, say 1, 0.75, that's over here, and substitute that in the same equation. We got W, we've got P, find the bias, in this case 0.75, and we got both our decision boundaries. And anything that is on the positive side of the red decision boundary and on the positive side of this blue decision boundary can then be classified as belonging to class 1, the black class, if you want. Weight and bias, the ones we just computed on the previous slide. And what we then want to do is we want to basically combine the two decisions that we're getting from these two neurons. We want to combine them using an AND operation. And for an AND operation, we'll have 2 inputs. You can play around with the input weights and biases. That's what's basically happening over here. What we want to do is we want the output from this second layer over here, A12. We want that to be 1 when both inputs happen to be 1. And if you experiment with it a little bit, play with different values of weights, of bias, what you'll discover is that weight 1, 1, and bias value -1.5 will do the job. And that's basically what this last table over here shows you. So if input is 0, 0, 0, 1, 1, 0, 1, 1, There's only one case in which if you choose a bias value of minus 1.5, the output will also be 1. In all other cases, the output will be 0, and that is basically what an AND gate does. And so that only took care of these 2 points of class 1. But as you can see, we have 2 other inputs that belong to the same class. And what we'll basically do is we'll repeat the same procedure that we did for these 2 points belonging to class 1. We'll repeat the same for these 2 points also belong to the same class 1. So what we'll do is we'll draw 2 decision boundaries, and we'll combine the decisions coming from both of them, just like we just did. So again, we pick 2 points, A and B. So this one is at 1.50 and at 1.51, A and B. Repeat the same steps. Not going to say them all over again because it's exactly the same. You end up with a weight vector, weight matrix. Pick a point on the decision boundary. In this case, we pick 1.5, 0.5, this one over here. Could pick any one. And use this equation to come up with the value of bias, in this case, minus 1.5 for this decision boundary. Then we have the 4th and last decision boundary. We pick 2 points on it. For the first one, 0.25, that would be this point. The second point D is 2.25, that's this one. Weight vector, orthogonal weight vector 0, 1. We got that right over here. Pick a point, any point on the decision boundary. In this case, we pick 1, 0.25, which is over here. Use the same equation. Knowing W and P, we find the bias, which evaluates to minus 0.25. Again, we want to combine the decisions from both decision boundaries. If the decisions are on the positive side, so basically we want to AND the decisions from these 2 neurons. We want to AND them together, just like we did for these 2 points. We want to combine them together. If the decision from both neurons for both decision boundaries is 1, then we want to classify a point as belonging to class 1. So got one neuron, another neuron, want to add an AND gate to it, like we did before. We're going to use the same values for weights and bias in the second layer. Basically, we're going to copy the same AND gate in the second layer, and that gets us that lets us classify these other 2 points also as belonging to class 1. Now there's one more step left. We need to combine the decisions from the second layers for these 2 points and these 2 points. So basically anything that is classified as class 1 over here, or classified as class 1 over here from here or from here, should be treated as class 1. So what we're going to do in the final and third layer is we're going to combine these 2 inputs that we have. We're going to combine them together using an OR operation. And that is what the third layer is about. And I'm just going to give you the weights and bias value for this 1 neuron of the third layer in order to perform the action of an OR gate, to act as an OR gate. And the weights happen to be 1, 1, and the bias value minus 0.5. Try it out, and you'll see that with these weights and this bias value, layer number 3 works like an OR gate. And so putting it all together then, these are the weights and biases of layer 1. These are the weights and biases of layer 2 neurons. And these are the weights and biases of layer 3. Layer 2, the one in which we have 2 neurons performing an AND operation. Layer 3, in which we have a single neuron performing an OR operation. And layer 1 with 4 decision boundaries. Okay, so multi-layer perceptrons can also be used for function approximation. Basically, you can use them to reproduce a function shape. So for this small demonstration, we have a two-layer neural network. We call it a one-to-one network. It's just the name we're giving it over here because it has one input, it has two neurons in layer number 1, and one neuron in layer number 2. And we're going to use these two functions as activation functions in layer number 1. So this is and layer number 2. Okay. So we're just going to I'm just going to give you, for a start, I'm just going to give you some weights that we're just going to use. So for layer number 1, we have weights 10 and 10, bias values minus 10 and 10 for the two neurons that we have over here. And for layer number 2, that's layer number 1, and for layer number 2, we have two weights. I'm going to set them to 1 and 1 and the bias value to 0. And let's apply different values at the input and see what we get at the output. And if you plot the input versus the output, you get this function that is shown over here, as long as for the range of values minus 2 to 2 for input values p. You can see that this looks like quite like a bit of a complex shape. Now, just to show you the things that you can do by adjusting these weight and bias values. So, for example, if you change the value of bias of one of the bias of the second neuron in the first layer, if you vary it between 0 and 20, these are how the shape. This is how the shape of this function will change. So it's basically this transition that you're seeing over here can be moved backwards and forwards. If you play with one of the weights in the second layer, you can affect the transition at the end, whether it goes up, how much up it goes, or whether it's actually a transition downwards in the function, by changing the value of the weight between minus 1 and 1. If you play with the other weight, so the other weight of layer 2, and you play with it in the same range, say between minus 1 and 1, then the shape of the function that we have changes like this. And if you play with the bias of the second layer, the output function changes like this. So you can see that we have, in this very simple neural network, we already have 6 parameters to play with. I just showed you what the effect of changing 4 of them will be on this slide. But you have 6 parameters to play with. So you can make plenty of adjustments to the shape of the function just with this very simply structured neural network. Now imagine the degrees of freedom that you could have if you have a much bigger, much larger, much more complexly structured neural network. And so then the question remains, how can I use a large neural network? How can I train it, discover the right weights and bias values to make it approximate any function that I wanted to approximate? Oh, and I should also note that in this case we were using the sigmoid transfer function in the first layer, and a linear pure linear transfer function in the second layer. These are also parameters that you can play with, that you can adjust. You can change the functions, and that will, of course, have different effects on the output. Now, the more neurons you have in the artificial neural network, the more closely you can approximate a function. And that gets us to the section on backpropagation. So much of this in this section is informational. I'll clearly let you know when this informational section ends. So this is just a little background on the backpropagation algorithm itself, which we do not derive over here. Okay. So let's consider that we have we have a multi-layer artificial neural network, 3 layers in this case, and the output from one layer is the input to the next, with the input to the first layer, A0, being the external input, P, and the final output from the entire network, from the mth layer of the neural network, is also denoted by simply A, no superscript or anything. So for training, we assume we have a lot of inputs and corresponding target output pairs. So just like before, for P0, this network we know should give us as target output T0. For P1, the output should be T1. For input P2, output should be T2. For input PQ, output should be TQ. So what we're going to do is we're going to apply each input, see how off the output from the network is, how significant the error is, and based on that, we'll basically be taking some action. And the first question is, how do we measure the error? And a very commonly used function for quantifying error is the mean square error function. And the mean square error function is basically the average difference between target and actual output squared, and the average of that over all possible inputs. The reason we take the square is that an error, the output can be off by a positive value or by a negative value. By taking the square, the amount or the magnitude of the error is guaranteed to be a positive value. Also, larger differences in the output are penalized more heavily. So this can also be written in vector form, like this. So the E over here, I think you should know by now, is the expected value function. And so if you want to write this in vector form for all Q possible input output target pairs, you can write it in vector form like so. Now the error is calculated at each iteration, and for that reason, what we're going to do is we can also add the iteration number as a subscript to the targets and actual outputs. So f of x or f hat of x will be used to represent the error function. In our case, we'll be sticking with the mean square error. And the backpropagation algorithm basically consists of two, assuming that we're using mean square error, consists of two functions. One function to update the weights. That's this blue function that you see over here. And instead of calling them, giving them boring names, like equation 1 and equation 2. I'm just going to call this one R2D2. And then we have another equation that explains how to update the bias values in bias vectors of each layer. And I'm going to call that equation C3PO. Alpha is, of course, the learning rate. And you can see over here that there are numerator terms in both of these equations that are basically the error function. And we're taking their derivative with respect to different weights, ijth weight of layer M, to update the ijth weight of layer M. The problem is in this slightly intimidating part of the partial derivative term in the end. How do we compute the partial derivative of the error function with respect to W and also with respect to bias terms? And the solution to this is to use the chain rule from calculus. Now the chain rule says that you can find the partial derivative of a function f with respect to a variable w by first finding the partial derivative of function f with respect to another variable n, which in turn is a function of w, and then find separately the partial derivative of function n in terms of w and taking its derivative with respect to w and then multiplying the two. As a simple example, let's assume that the function that we're dealing with, f of n over here, is cosine of n, and let's say n is then further a function of w as specified like this: n is equal to e to the power 2w. So finding the derivative of cosine of e to the power 2w in one step may be a bit much, and so this is a situation in which the chain rule comes in very handy. So what we'll do is we'll find the derivative of f, meaning cos of e to w. We'll hide this e to w part. We'll treat it as a variable n, and we're just going to take the partial derivative of this function cosine of n with respect to n, and that'll give us the first term. And then we take this much simpler function n in terms of w and find its partial derivative with respect to w, and then we just take the product of the two. The partial derivative of cosine of n with respect to n is minus sine n. The partial derivative of e to the power 2w with respect to w is 2e to the power 2w. Now, n, of course, can simply be substituted with e to the power 2w, and that gets us this expression over here. And this is how you can apply the chain rule in such situations. And we will be doing the same thing for every mean square error function f with respect to every input j to every neuron I of every one of the m layers. That'll be many times. And the same thing for bias. To update bias values, we will take the partial derivative, we'll apply the chain rule to find the partial derivative of the mean square error function by taking the partial derivative with respect to every bias of every neuron I in every layer M. So again, that can happen many times depending on the size of your neural network. Now, we know that the output, the intermediate output, the input to an activation function, N, can be written like so. This is basically the action performed by a neuron, the ith neuron of the mth layer. Ith neuron of mth layer. And so you can begin by first finding the partial derivative of n with respect to w, and that's actually quite easy because this term the second term over here is independent of w, so this just goes away, and all you're left with is the summation term, and these are just many terms, m minus 1 terms just being, s terms just being added up, and so all of these terms except one will become 0 because all of them except one will be independent of this one specific weight that we're interested in. And the only thing you'll get is the corresponding coefficient that's being multiplied with that weight. That's it. That's what we have over here. And if you take the partial derivative with respect to a bias value, the bias value of the ith neuron in the mth layer, you can see that it's quite straightforward. It'll just end up getting a 1. And that leaves us with the other term of the chain rule, the partial derivative of the mean squared error function with respect to n. And there's a name for that. We call that sensitivity. When you take the product of the two, this together with the appropriate partial term that we got up here, when you take the product of the two, you get the partial derivative that you saw in the R2D2 and C3PO equations, which is this sensitivity times A, or just sensitivity when you're talking about partial derivative with respect to bias. So if you plug these two terms back, if you plug the first term back into the R2D2 equation, this is what the new updated R2D2 equation will look like if the error function that you're using is a mean square error. And just like that, the C3PO function will have an updated term over here. And this is the updated C3PO function. Now I'm not going to get into where this comes from because this is part of what we're not doing in this section. That would be part of the derivation of the backpropagation algorithm. So this, you have to take my word for, is how you compute sensitivity for layer number m. And you can see that it depends on the sensitivity of the next layer. So if you're computing the sensitivity for some, let's say, layer number 2, in order to do that, you need to find the sensitivity for layer number 3 first. And you need to use the weights for layer number 3, the next layer. For the last layer, of course, things will look a little different, and sensitivity for the output layer, the last layer, will be computed like this, like so. and so the thing that's different over here is the appearance of the error, the difference between targeted output and actual output that we got. And we can also write that in vector form, like so. And with this, we come to the end of the informational section on the backpropagation algorithm. So, in essence, there are two phases to the backpropagation algorithm. First, there's the forward propagation phase, in which you apply your input, call it A0, and you let that input ripple through all the layers of your neural network towards the output. We've done that many times now, so there should be no mystery over here. It's basically us applying this function to each layer. Plug in input, either P or from whatever you're getting from the previous layer. Use the weight matrix and bias vector to compute what is actually just the intermediate output, NM. Give that as input to the activation function, and that is the output from that layer. We do that for layer 1, 2, 3, 4, all the way to the output layer. And once we're done with that, we use the backpropagation algorithm to update all the weights and biases. The activation functions do not change. They're selected in the beginning initially, and they stay the same. They're not changed out. They're not trained or modified in any way by the backpropagation algorithm. The selection, the choice of activation function is basically fixed, part of the architecture of the neural network. So, and this is how we begin. We begin by finding the sensitivity of the output layer, like this. And once we do that, once we have the sensitivity for the last layer, we compute the sensitivity for the preceding layer. So, meaning for layer m-1, and for layer m-2, all the way back to layer number 1. So this happens in reverse order, and that is where the backpropagation algorithm gets its name from. Once we have all the sensitivities, we can then use them to update the weights and bias values of all layers. So WM K+1 is basically the K+1, the next set, the updated set of weight matrices. So if you go back to, for a partial example, I should say, if you go back to the 1-to-1 network that we had, let's say we want to approximate this function g, 1 plus sine of p pi by 4. And we want to approximate that for a range of input values between -2 and 2. And since we have nothing better to do, nothing better to to start with, we'll initialize the weights and biases of this 1-to-1 network. We'll initialize them randomly, and here's a set of random values that you can start off with. Now, just to understand what this function is that we're trying to approximate and what will happen after the first iteration, this over here, the black line that you see, this is the function that we're trying to approximate. Now, initially, with these random weights and biases that we chose, this blue line is what this network is actually doing in the beginning. It's not doing much. It's nowhere near to the function that we're trying to approximate. And if you want to look at a couple of sample values, so for these input values in the first column, we want to see the values in the output that you see in the second column, the function g. But what is actually happening with these initially randomly chosen weights and bias values is what we're actually getting is what you see in the third column, 0.446 for everything in the input range -2 to 2. So it's not doing much. So to start training the network, we can randomly pick any input. So let's say you pick for the first input, you pick p equal to 1. So that would be this one over here. And it should give 1.707 at the output. That's what we want to happen. What will actually happen is we'll get this. So input comes equal to is called A0 is equal to set equal to 1. So the output from the first layer is quite simply this. So substitute 1 in here. We use the weight and bias vectors in this case. You do the math over here, you get this thing that this vector becomes the input to the activation function. We've chosen the log sigmoid function over here. You do that, apply that function to it, you get this thing and these output values. These are the output values from layer 1 and the first iteration. These become the input to the second layer. So input to the second layer. And the second layer uses a pure linear function. You evaluate all of this. So you can see these values being plugged in over here as input to the second layer. Do the math and you end up with 0.446. That's where that's where this 0.446 comes from, and you can try out any of these other input values with the weights and biases that we have. This one-to-one network isn't doing much. It's basically spitting out the same output values. That obviously needs to change. And so we compute the error, the difference between what we wanted as output and what we're getting as output, A. And what we want as output is this thing. And what we're getting from the second layer as output is A2, or 0.446. And the difference between these two happens to be 1.261. So just a note again, this is not A square, this is the output from layer number 2. I know this might seem a little tricky, but you have to understand from context when a superscript is denoting an exponent and when it is denoting a layer index. Okay, so first step, calculate the derivative of the transfer function. So find the derivative of transfer function with respect to n. So you do that, and for this particular function, you end up with this thing over here. For the second layer's transfer function, that's pretty simple. It's a pure linear function. The derivative of that is 1. So then we start with a backpropagation algorithm. So we find the sensitivity for layer number 2. And we end up with minus 2.522. Then we find the sensitivity for layer number 1. That's the equation for that. And do the math, do it all at once using matrix operations. Not going to walk through each and every step over here, but you end up with these sensitivity values for layer number 1. S2, S1. Now that you have S2, use the R2D2 equation, that's what this is, correct, to get new weights. So these are the weights that we had. This is the learning rate alpha. This is S2. And This over here are the output values from layer number 1, A1, transposed. Do the math, and you get these new weight matrix. You get this new weight matrix. We also have to update the bias value for layer number 2, and for that we use the C3PO equation. S2, learning rate, old bias value, give us the new bias value. Do the math and you end up with this new bias value. All of this was for layer number 2. Now let's step back to layer number 1. And for layer number 1, update weights, update bias. And this is the first iteration, the first use, the first pass of the backpropagation algorithm for this extremely simple example. You can see it took a lot of operations to do. And if you were to continue this process, you would now apply another input, another one of the possible input values for P. So basically other values in the range -2 to 2, and repeat the whole thing again many times until the output error, the error that you're seeing in the output, becomes acceptably small for you.